Dear all, I am Dr. V. Malati, Associate Professor, ECE Department, SR University, Varangal. So, I am going to simulate ultrasound wave propagation and ultrasound imaging. Code for this is going to be written in Python and it will be simulated in the Google Colab platform. So, let us start. Simulation, ultrasound, wave propagation and ultrasound imaging. This experiment includes ultrasound wave propagation simulation, echo generation from issue boundaries, A scan imaging, simple B scan image formation. So we can copy and run this directly in Google Colab so that I am getting, and output is also I am getting. So now I will explain the code. So here is clear step-by-step explanation of the ultrasound wave propagation and imaging simulation code. This experiment simulates ultrasound pulse transmission and echo formation from the tissue reflectors, A scan imaging, B scan imaging. So first we have to import the library. So for NP, it is used for numerical calculation, that is arrays, time vector, mathematical operations, and matplotlib. It is used to plot graphs and images. So graph means we can plot parameter versus parameter, and then histogram, box plots, bar charts, and so on. So first one, basic ultrasound parameters. Here the parameters given are C equal to 1540. That is speed of the sound in soft tissue. It is mentioned in meters per second, and then Fs is equal to 20 e power 6, that is sampling frequency 20 megahertz. So 20 into 10 power 6. And then F naught is equal to 2 into 10 power 6, that is transducer center frequency 2 megahertz. T underscore max, it is equal to 100 e power minus 6. This is the observation time, 100 microsecond. So for this meaning I am telling you, for each parameter C equal to 1540. The speed of sound in soft tissue is equal to 1540 meters per second. This is a standard biomedical value. So how we are defining 1540? It is not our own wish, and it is as internationally accepted value. That is why we are defining the value 1540 for C. And then Fs is equal to 20 e power 6. So it is the sampling frequency 20 megahertz. Normally sampling frequency will be very low. So till now for the previous experiments we have taken very small frequency, that is if sampling frequency is a very low value, but here we are using very high value. Why this much high value? Because ultrasound frequency is high, that is 2 megahertz. So sampling must be much higher to capture the waveform accurately, and then F naught equal to 2 into e power 6. Transducer center frequency is equal to 2 megahertz. And what is transducer center frequency? This is the frequency of the emitted ultrasound wave. And then T underscore max is equal to 100 e power 6. So total, T means total observation time. It is equal to 100 microseconds. So e power minus 6, 10 power minus 6 microsecond. This determines how deep we can see. And then T equal to NP dot A range open bracket 0 comma T underscore max comma 1 by Fs. So the time axis, that is x axis, starts from 0 and then ends with 100 microsecond. And in between the partition is done by 1 by Fs. So 1 by uh, uh, 20 megahertz. So it creates the time. So this statement creates the time axis. Step size is equal to step size. So uniform interval. So in the step of every point is added. Step size is equal to 1 by Fs. So time increases in very small interval because it is 1 divided by 20 megahertz. So it is very denominator is high value, so that the total value is very small value. It generates ultrasound pulse. So in this case, how it is generated? Pulse width equal to 2 into e power minus 6, that is 10 power minus 6. Pulse is equal to np dot sine 2 pi f naught into t into exponential, that is e power minus t, t underscore pulse underscore width power 2 divided by pulse width divided by 5 the whole square. So how we will write and what is the meaning? This equation creates a Gaussian modulated sine waveform. So the first part sine 2 pi f naught t, and this is the 2 megahertz ultrasound carrier wave. And the second part, it is e power minus t underscore pulse width the whole square divided by pulse width divided by 5 the whole square. So this is the second part, and this is a Gaussian envelope. And why it is used? Normally, real ultrasound pulses are short burst. They are not continuous waves. So, Gaussian limits the sine wave to a short duration. Simulated tissue reflector. Next one. So depth is equal to 0.02, 0.04, 0.06. That is 2 centimeter, 4 centimeter, 6 centimeter. And then reflectivity is equal to 0.8, 0.5, 0.3. This simulates 3 tissue boundaries at 2 centimeter, 4 centimeter, 6 centimeter, and then reflectivity represents how strong the echo is. Higher reflectivity means stronger echo. So then echo signal formation. Echo signal formation. So echo signal is equal to np dot zeros underscore like t, and it creates an empty signal, initially no echo, and then loop through echo reflector. So for t comma r in z open bracket depth comma, reflectivity. And what is the meaning for this statement? For each depth and reflectivity, the round trip delay, it is equal to 2 into d by c, and ultrasound travels to reflector and back. That is why. So normally delay time, it is distance by velocity. Delay means time. So time equal to distance by velocity. But here 2 into delay by velocity. While 2 means ultrasound going from the source, and then it is reflected back and it is reaching the source again. So two equal distances, two-way paths are followed by the ultrasound. That is why one time means it is two-way travel. So 2d by c. And it converts time to sample. That is, delay underscore samples is equal to integer open bracket delay into fs. Since the signal is digital, delay must be converted into sample index and then insert echo. So echo underscore signal, it is delay underscore samples. That is delay underscore samples plus LEN length open bracket pulse, and then plus is equal to R into pulse. So this shifts the transmitted pulse by the delay amount and multiplies it by the reflectivity, that is amplitude reduction. So we get the delay echo at correct times and then a scan signal. And what is the code for this? A scan equal to echo signal. Then a scan shows amplitude versus time. Each spike corresponds to a tissue boundary. It converts time to depth. So depth axis is equal to T into C by 2. We reverse the delay equation so that D equal to CT by 2. Now horizontal axis becomes depth instead of time. This is how real ultrasound machines calculate depth. And then B scan simulation. So the formula is num underscore scan lines is equal to 50. So we simulate 50 scan lines like moving through sideways. Then add small random variations. Random variation is equal to NP dot random normal. In open bracket 0, 0.002 and comma LEN depths. Why it is stated here like this? To simulate small irregularities in tissue shape. Otherwise, all scan lines would look identical. So we have to build 2D image. Each scan line produces one A scan. So we store all A scan in B underscore scan up dot append NP ABS open bracket echo. Finally, convert into 2D array. So B scan equal to np dot array open bracket B underscore scan, and then display B scan image, that is plot plt dot im show open bracket B scan dot t comma cmap CMAP so x length equal to 0 comma num scan lines comma depth axis minus 1 into 100 comma 0 aspect equal to auto CMAP equal to gray. And now what is the meaning? X axis scan line number, y axis depth, intensity is echo amplitude. This creates a grayscale ultrasound image, and then bright is equal to strong reflection, dark is equal to weak reflection. So this code explains pulse generation, short ultrasound burst, wave propagation using speed of sound in tissue, time of flight principle, depth calculation using echo delay, A-scan imaging, one-dimensional echo representation, and then B-scan, two-dimensional grayscale image. So finally, the conceptual summary is transmitter to pulse, then tissue reflector, then echo returns, then measure time delay, then convert to depth, then create image. So how we will get the diagrams here? See, transmitted, ultrasound pulse. So amplitude versus time in microsecond, and then A-scan ultrasound signal. So that is resembling like this. It is drawn time in microsecond versus echo amplitude, and then A-scan depth representation. It is drawn depth in centimeter versus echo amplitude, and then simulated B-scan image. So it is scan line, and it is depth in centimeter, and it is echo intensity. So first of all, we have to import the NumPy like Python library, and then matplotlib. So this library function will be imported from the pyplot module. So basic ultrasound parameters are C is equal to 1540 and Fs is equal to 20 e power 6. F0 equal to 2 into e power 6. Tmax is equal to 100 e power minus 6. And the code is T equal to np dot arange open bracket 0 comma Tmax comma 1 by Fs. So this time axis is starting from 0 and ending at Tmax. So this maximum observation time is taken as 100 into 10 power minus 6. So 100 microsecond, and this 100 microsecond is divided with, so how it is divided? So already 1 by Fs is equal to, we know, 1 by 20 megahertz. So this 100 microsecond will be divided by this value, so that how the second point, third point will be determined. So C is equal to 1540 means it is the speed of the sound inside the soft tissue, and it is internationally accepted biomedical value. And the Fs is equal to 20 e power 6, that is sampling frequency 20 hertz. And why this much of high sampling frequency is adopted in this experiment? Because ultrasound frequency is high, 2 megahertz, so sampling must be much higher to capture the waveform accurately. And then F naught is equal to 2 e power 6, and this is the, and next one, transducer center frequency is equal to 2 megahertz. This is the frequency of the emitted ultrasound wave, and then T max is equal to 100 e power minus 6. It is the total maximum observation time. It is equal to 100 microseconds, and this determines how deep we can see. How deep it is visible to us. And then the code is T equal to NT dot A range open bracket 0, T underscore max, 1 by Fs. It creates time axis. So step size is 1 by Fs. This time increases in very small interval. So the step size is very small. And finally, this equation generates a ultrasound pulse. And pulse width is equal to 2 e power minus 6. And the pulse is equal to np dot sine 2 pi f naught into t, and np exponential e power minus t minus pulse width square divided by pulse width by 5 the whole square. And this is the Gaussian modulated sine wave. So the first part is sine 2 pi ft, and this is equal to 2 megahertz ultrasound carrier wave. The second part is e power minus t underscore pulse underscore width square divided by pulse underscore width divided by 5 the whole square, and this is the Gaussian envelope. And why these statements are included here? The real ultrasound pulses are short bursts and they are not continuous waves. So the Gaussian limits the sine wave to a short duration. So simulated tissue reflectors, depth is equal to 0.02, 0.04, 0.06. It is a vector. And then reflectivity is equal to 0.2, 0.5, 0.3. So it is also a vector representation. This simulates 3 tissue boundaries at 2 cm, 4 cm, 6 cm. Reflectivity represents how strong the echo is. High reflectivity means stronger echo, and then echo signal formation is done by using this expression. Echo underscore signal, it is equal to np dot zeros underscore live t. It creates an empty signal. So initially no echo, and then loop is occurring through each reflector. For D, R in Z, open bracket X, reflectivity. So round trip delay happens. So this delay is equal to 2D by C. Normally delay time is equal to distance by speed, but here 2 into d by c. What is the meaning? once if it is generated by the source, it will travel a path, and after getting reflection, the reflected wave travels the same path to reach the source. So the same distance is passed by the ultrasound wave two times. That is why 2D by C. The ultrasound reflects to the reflector and back. So next one we have to convert time into samples. So delay underscore samples it is equal to integer open bracket delay into fs. Since signal is a digital, delay must be converted into sample index. So insert echo. So echo underscore signal open bracket delay underscore samples is to delay underscore samples plus len pulse. It is then plus is equal to r into pulse. So open bracket is to length time minus delay samples, and then this shows that this expression shifts the transmitted pulse by the delay amount and multiplies it by reflectivity. That is, if it is reflected, then automatically amplitude becomes reduced. So, we get delayed echoes at correct times. Then a scan signal, it is represented by A underscore scan is equal to echo underscore signal. A scan shows amplitude versus time. Each spike corresponds to a tissue boundary and convert time to depth. Depth underscore axis is equal to T into C by 2. We reverse the delay equation. That's all happened here. That is why D equal to Ct by 2. Now, horizontal axis becomes depth instead of time. And this is how real ultrasound machines calculate the depth. And then B-scan simulation. So the equation is num underscore scan line is equal to 50. So how we get a B scan? We simulate 50 scan lines like moving probe side waves. Add small random variations. So random underscore variation is equal to random dot normal open bracket 0, 0.002, length index, and then echo is equal to np dot zeros underscore live t. And why it is given? To simulate small irregularities in tissue shape. Otherwise, all scan lines would look identical. Then we have to build 2D image. Each scan line produces one A scan. We have to store all A scans in B scan underscore B scan dot append open bracket NP ABS echo. So finally convert into 2D array. Then B scan is equal to np dot array b scan. It displays the b scan image. So that is what here plot dot figure size is equal to 6 comma 6, and then image show how it is shown. So we are having the outputs here. So this is shown in the grid, that because we have started with the grid plot. Thank you.